Okay. So good morning, and today we continue our study of the statistical mechanics of ideal gases. This is the second lecture, and today's lecture will be mostly on the ideal Bose gas. And let me just write down a couple of formulae from last lecture. And yeah, go ahead.
It's possible that rows behind can't hear you.
Which rows? The last rows cannot hear me. Okay, I'll speak louder. No mic, please. I mean, I'm already feeling tethered like a cow to a post or something like that. And just let me write two formulae and then start my lecture. Okay. So first thing to point out is that last lecture I was just very cavalier. There was a log and that will shift the thing by the thing. I just wrote G3 half here instead of okay. I wrote 3 half here instead of this thing, and then that I have to subtract 1 to get the next one, so the error propagated. So these are the correct this things. And so Gn of z is this integral 1 by gamma of n integral 0 to infinity dx x power n minus 1 . Is it e power minus x or e power x? What is it? Okay. And lambda is the thermal wavelength, so it is just h by 2 pi m kbt power 3 half. Okay, so these are some definitions, and little v is v by. Okay, so yeah. Okay, v by n. Any other things? And z, of course. Yes. Okay, so let's look at this thing again. And so this the two extra terms, that is this, is coming from the p equal to 0 or ground state contribution. Okay, is written out explicitly. Okay, so this term, the two second terms, which are not in terms of G5 by thing. Okay, so first point is that when z is less than 1, okay, the second term vanishes in the thermodynamic limit. Okay, in particular, take v to infinity. Okay, so you can see that 1 minus z will be some finite number. So log of that will be finite, and so when v goes to infinity, that goes off. But when z hits 1, we have to be careful. So we get that's the log of 0 is infinity. So it's infinity by infinity. We have to handle it carefully. That's why we are putting this term, and we will work out what that is. Okay. Same thing is true for the second in the second formula, but we can rewrite the second formula in a slightly different way. So when multiply by capital V, okay, on this, and so you will get Okay, and that factor of v will go away, plus z into 1 minus z. Is that all? Okay, so that goes off. So this is what we get. Okay, and so so let's look at the first term. So we worked out the properties. In particular, g3 half of 1 is finite. And is equal to what? Zeta of 3 by 2, which is around 2.6. Okay, so it's some finite number. That's all that is important. Okay, so what we will do is, yeah. So the point here is that if you look at this form, so there are two forms. So let me go back to the first form of the same thing. So if you look out here, the quantity. So let us define. Okay, so let us define. Okay, 1 by V naught. Okay, which is a function of temperature, by the way, is equal to G3 half of 1 divided by lambda cubed. Okay, the temperature dependence is there because lambda depends on T. Okay, it's a thermal wavelength. So if you divide this thing, I'll rewrite formula 1 as 1 by V equal to 1 by V naught plus, okay, Z okay. So of course this is a function of temperature. Okay, Z is also a function of temperature through these things, but I just want to say V naught is not a fixed number. It varies as we vary temperature. Okay, so the thing is that, so in the grand canonical ensemble, of course, the number of particles is not fixed. So we would like to, so usually what the setup is, that we consider an ideal Bose gas with n particles My pen is behaving funny. Okay. So, but then we say that in the grand canonical ensemble, this n should be identified with what? Average value. Okay. So n goes to expectation value of n in the grand canonical ensemble. Okay. So, but we can also turn it around and ask, we can say that in the canonical ensemble, what will be the value of mu? Okay. So we can invert. So in the canonical ensemble, where n is fixed, Z and hence mu, the chemical potential is determined by the equation implicitly by the equation which we wrote. We'll give it a number, maybe this is star. Okay. Nobody said anything, I just messed up somewhere. Did I mess up? Yes, I did. This is not the equation, right? It is, there's a factor of G3 of Z by G3 of 1. Again. Now it is okay, right? Because there is no Z. Is this fine? Okay. Star or the other equation. And so the point is, so there are two cases to consider, or situations to consider. Okay, and so the first one, when z is less than 1, strictly less than 1. Okay, then the chemical potential is determined by let me write it now, not in terms of that equation, but write it a little bit more. So n and v are given, and this is equal to this is the equation. And so when is z, so now the question is, when is z less than 1? Okay, so if you look at this expression, the right hand side, we know that RHS, okay, is always less than or equal to G3 half of 1 by lambda cubed. How do we see that? So you look at this function G3 half of z, it's a monotonically increasing function. If you do this plot, okay, so and so say, let's say this is the value 2.6 zeta of 3 by 2. This is the value, and let's say this is 1 and this is 0. It goes something like this. It's easy to prove that it's monotonically increasing. Okay, so it's something like this. It goes and saturates. Okay, so RHS is less than or equal to this. Yes. So it will be strictly less than that thing. So now you can see that this equality which we wrote happens only, so we need, in other words, 1 by V must be less than this quantity we called 1 by V naught, if you remember. Okay. So this is the condition. Okay, so the density should be less than, so this is number density is inverse of this thing. Okay, so what it says is that the number density should be less than this some funny density which is fixed, which is a temperature dependent thing. We are thinking of T constant. So this is the condition. So that's when Z is. Is this clear? So we've got the condition, and the equation that we have to solve is this equation for Z. Of course, it's a messy equation to solve, but you can always numerically solve it or whatever. Okay, so that's not a problem. We can solve it. So the second case, okay, is V being now less than V naught. So this is okay. So here this is the dense gas. Okay, low temperature. Okay, so in this case, so coming back to this, so now you can see that so here is where there is a here what happens is that, so we'll make a claim and we'll try to say Z equal to 1. Okay, so and now I'll go back and write the second form of the equation, which was here. Okay, where I'll write n equal to plus. Okay, so we get a uh, no, I want to write it not this way. This is the equation. Okay, so this is the number density, and so now, so the point here is this is not going to change now. So this is identified with the contribution of particles with p not equal to 0, not the ground state. Okay, so now is the thing. So instead of writing something like this, so we have so now earlier in the thermodynamic limit, we were saying this term was vanishing, but now z is 1. So what we have to do is to say that no, actually this term that there will be, so this term is replaced by the density or inverse density of particles with p equal to 0 in the ground state. And we can make a little bit more concrete thing. We will say that z minus 1 goes as 1 by v. So if you're going to approach 1, it should go as 1 over v, so that when you take the thermodynamic limit, it gives you something finite. Okay, so this is what happens when z equal to 1. That you find that you have a finite fraction. This is a density being. It's not like 10 particles are there. It's like there's a huge fraction, macroscopic fraction. Something like maybe 1 by 100 or 1 by even 10 power 4, 1 by 10 power 6 also. But that's fairly of the full gas is in the ground state. So it's actually better to think of this system as a two-component system. One with the set of particles in the higher excited states, and the other component is just all in the ground state. Okay, so it is better. Yes. No, it cannot go by 1 by v square, then that term will be 0. It has to be strictly going by some constant times v. Okay? No, nothing will work. Either if it is v power half, then it will go to 0. If it is something greater than that, it will blow up. So it has to go like v. That's the only way, if you're going to take it as a limiting process. But it's better to just say that forget this whole term and say that there's a fraction, finite fraction, and this is telling you what is a fraction. Okay. So in other words, in the thermodynamic limit, let me just write this. Okay, so this is what we want. So it is better to think of the ideal gas as consisting of two components, coexisting components. Okay, first component is one consisting of particles with p greater than 0, and the second one with consisting of particles with 0 momentum. This is what. Okay. So we'll give a name to this guy. So this guy is this phase, we'll call it the Bose-Einstein condensate. Okay. And this phenomenon was predicted by Einstein. Okay. And it's called what is it called? Bose-Einstein condensation. Okay. So now there are several interesting questions to ask. The first question is, why is it possible, for instance, to have a finite fraction not just in the first zero in the ground state, but how about the first excited state? You can prove that that cannot happen. Okay, that won't happen. So really, it can only go to the ground state. This is just some calculational thing. You can prove that. Okay, so that's the first point. Second point to ask is this answer dimension dependent? So we said we are in 3 space dimensions, so we got G3 by 2. So suppose we go to say 2 dimensions, ideal gas in 2 dimensions. Can that happen? So now what happens to an ideal gas? So if you go back and look at the thing, you will see that G3 half will become G1, I think. It will come down because it came from the density of states, right? There was a p square, and that you wrote as square root of epsilon. Okay. So now what will happen is that the density of states will come down by 1 power of p. So it will just become, so what you will see is that it will become G1. Okay. But what is G1 of 1? It's infinity. So in 2 dimensions, we should not expect Bose-Einstein condensation, because it's unbounded. So now there is no problem in fixing me. What was the problem? We came here, we looked at this equation, and we saw that because G3 half was bounded, it reached some finite number. Because of that, we couldn't satisfy this equation until we said that, okay, whatever is not fitting this formula, whatever remains is in the ground state. But if this was unbounded, if it goes to any value below 1, okay, then there is no issue. This you will not see Bose-Einstein condensation. So it's a very dimension dependent thing. Okay,
So the number of particles in the ground state, it is not fixed.
It is fixed. It's fixed by this equation. By this equation, this is not the number of particles. Yeah, it's number density. Number density is fixed. So this will be equal to, I can write it something like this, N naught by V. Let's put capital N. Where N naught is the number of particles in the ground state. Okay. So I'll pause here for questions or comments.
So this number of particles is high enough so that they form a fraction.
Yeah. So we can actually find out what it is, etc. We can compute these numbers, and okay. So we can do that. But I don't. So today, of course, Einstein did not think it would ever happen. That we'll get to experiments where we could, if you work out what the temperature is, I'll discuss what the critical temperature is. It's fairly low. Okay. So you should understand that in the temperature scales, there are certain scales which are from practical viewpoint, and these numbers you should know. One is the liquid nitrogen. When does it become this thing? So that's around what, 80 Kelvin or something? Okay. I am not so good. So 80 Kelvin, right? So one set of experiments. So if you want to bring in temperatures down to 80 Kelvin, all you can do is put it in something where you use liquid nitrogen. The second level of sophistication is to go to liquid helium. What is the temperature there? It's about 4 Kelvin. Okay, so 4 Kelvin again is something which one can achieve by using liquid, provided you have liquid helium. turns out that looks like the helium resources in the world is depleting, and now pretty soon there will be competition for that. But nevertheless, but what you need, temperatures that you need are not that way, they are in millikelvin. Okay, so one needed advances in lowering of temperature, and the first advance was something called laser cooling. Okay, which brought down the temperatures further, but that was also not good enough for Bose-Einstein condensation, and then they needed more tricks up their sleeve. Okay, if I vaguely remember, the most important trick in that whole thing was to switch off the cooling. Okay, so that all the faster particles escape, and then you let them thermalize, and so the temperature falls down on its own. Okay, it's I mean, it's pretty clever. You need to have a bottle, etc. Bottle means don't think of water bottle. Okay, so and but the whole point here is that we have finally observed Bose-Einstein condensation, and the number of particles in that thing are not Avogadro's number, but I think they are like I don't know. I'm not very good with numbers, but I think it's more like 10 power 8, 10 power 10. Okay, but it's still fairly significant. Okay, so again, people won Nobel Prize for this thing, but what you have to appreciate is that the experimental advances, they are very, very clever, extremely clever things people do. So there are two steps from below helium. One is laser cooling, and the second is what these people did. Okay, only a couple of labs did it, and they get the Nobel Prize for doing it. And so please read up the story of that thing, and maybe I'll share something. So today we have observed Bose-Einstein condensation. Okay, so let me just I mentioned that that's a critical temperature. So far kept T fixed. Okay, so if you remember V naught, recall that V naught. Okay, so recall that V naught depended on temperature. Okay, and what was V naught? Somebody tell me. Is it lambda cubed by G3?
Lambda cube by G by 2.
Okay, and so lambda is proportional to uh, h by something, so it's proportional to t power minus half. Okay, so this implies that V naught is proportional to t power minus 3 by 2. Okay, so what was the condition? So condition for z less than 1, what was it? It was v v v v less than V naught, is it? V greater than. Ah. Okay, of t. So suppose, so now you can see that as you, so now we have, what we are going to do is we'll keep number of particles fixed. Okay, so we keep n v fixed. Okay, and start lowering t. Okay, so what is going to happen to V naught? Will it increase or decrease? It will increase. Okay, so as you this thing, there will be, so there will at some t equal to Tc, V equal to V naught of Tc. Of course, it depends. So Tc depends on what is the number density you are working with. Okay, so this is what happens. So for T and for T, this defines Tc. Okay, so for T less than Tc, what happens? Z equal to 1. Okay, and we have a Bose-Einstein condensate. Okay, is this clear? Okay, so and then we have to think in terms of two phases, two component systems rather than one component system. And so this is what happens. And so now, I mean, so standard exercise would be, put in realistic numbers for n over v, for n and v in some sense, and compute TC for some gas. Okay, you can do that. Okay. Before this thing, so in those days, so was there any evidence for Bose-Einstein condensation before we actually saw it happen in the lab, right? So the evidence, indirect evidence existed. Was seen in the helium-4 system. Okay, so the helium-4, liquid for helium-4 is a system of bosons. Okay, okay, which underwent something called the lambda transition. Okay, there is a helium-3 system. It's very similar, but is made up of helium-3 is fermionic. So you can think of it as a gas of fermions, where this transition does not happen. Okay, so the interpretation was in this thing, the lambda transition is Bose-Einstein condensation. Okay, it turns out that there were certain properties of it which is agreement with it, but not everything. There are more details in the story. Okay, but so this was indirect evidence, but direct evidence required. Okay, so direct evidence came much later, right? Okay, so see Nobel lectures. I don't know which year. Okay, so now let us study what is happening. So let us look at. So yeah, I didn't prove for you that fermions don't condense. Why doesn't the same thing happen? And that is because if you remember the fermion integrals, they were just one sign being flipped, right? But then in the summation, you get so you get a minus one power L or something like that. So it's an alternating sum. So F3 half is diverges. Okay, so there is no issue. So there's nothing strange happening there. So there is no Fermi-Dirac condensation. That cannot happen. There's no issue in fixing mu. Further, I already told you that mu can take values over the whole real line. Okay, but for if z being 0 to 1, that means mu can take only negative values up to when it becomes 0, it becomes 1. Okay, so let's do some more details of these things. Okay, so first, so let us write now. Yeah, so I need some equations. So I'll look it up. So I won't forget something. Do I have it here? I don't know. No. Okay, so yeah. So what are the properties? Okay, so okay, there is a critical temperature. Yes. If you have a comment to make, you can make it to everybody. You don't have to make it to him alone. Yeah. It's not relevant to the class. Okay. Then it's fine. Don't share that. Okay. So now we can ask, what is the uh yeah, so maybe I should do it with respect to T. So we have a TC, and then we can do, fraction or whatever. I'll draw a curve and then I'll explain what the axis is. Okay, so I'll draw something. So this is 0 to 1. So y-axis is the fraction of particles in the ground state. Okay, so until Tc it is 0. Okay, then Bose-Einstein condensation starts. So as you go at Tc, this thing, so below that it will start increasing, and then at 0 temperature we know something, that everything goes to the ground state. Okay, so it will go to 1. So you get some. So this is just a curve. Okay, so I mean the point I was trying to make about the difficulty in achieving the Tc is that it's very clear that if I went somewhere here, the fraction will be larger, but those are how low you can go is not completely within your control. It depends on the experimental setup. What's the best you can do? Okay, and people have gotten really good at this. So this is so this is like a phase transition, right? So this is a phase transition. Okay, so now we can ask, what is the order of the phase transition? Okay, now you can take a guess or whatever. What do you think it would be?
And T equals to TC is going to be second.
Second order. Okay. Any other choices? Okay. Turns out that it's a first order transition. Okay. So maybe I'll give in the next problem set. Okay, so there will be some latent heat, and so we have to use same thing like we did for earlier case we had done, right, for latent heat. So there'll be a latent heat kind of thing. You can just work out using Clausius-Clapeyron equation, etc. So it's kind of straightforward, but but it needs some calculation. Okay, so the third one, I need some figures, so I will look up in the book. So this is a book by uh, Kersen Huang. It's a fairly advanced book, okay, but it's a nice book. So all of it, I think, might be too high for you guys. So I just want some nice. There's lots of nice pictures. So I'll draw some more pictures. So we can draw the PT diagram. It goes like this. Okay. So here is the gas phase. Okay. And the key point here is that I'll draw some, let me change color for a moment. Okay. There's nothing in this region. Okay. The, the condensate exists only on the line. Okay. And this is nothing. Nothing here. You don't achieve that. Okay. This is one picture. And I want to draw next picture, which again, these are things we can prove. So let me just draw one more picture and then write a bunch of formulae for you. Okay, so we should try to do this. So let's do specific heat. Okay, versus temperature. There's some Dulong-Petit law or whatever that will happen at high temperatures. So you start like this, it goes up. Okay, and this is Tc. Okay, these are things we can prove. We don't, and then it goes on to its limiting value. So this is just okay. So that's a kink. Okay, so now I'll finish in a couple of moments. I'll with an exercise, which is basically your next assignment. So exercise. Okay, show that. Okay, so now I'll start copying things. Okay, so many of these things were straightforward from G of 3 by 2, I guess. Okay, so the top line will always be T less than Tc. Bottom line will be this thing. Okay, so F by NKBT. Can someone look up this subscript? My eyes aren't good. Is this G3 by what is it? This? These are all by last number. Yeah. That one will be 5 by 2 by 3 by 2. See, my eyes aren't good. Ah, I'll take care of it. Thank you. Of 1. I'll just write one more and then I'll put more in there. Okay, so you can see that you have to give the fact that you are at a phase transition. You have to give. You need to give how things behave on both sides. So there, you can only give piecewise continuous functions, and that's what this is doing. And so you can see that we can just go back to the standard definitions and work out what f should be, what s should be, etc. And so this is so you will have, and you can see that we can also get. So for me now, for instance, I've written this, but offhand, if you ask me where is the log z coming from, I say that I have no idea. But if you do it and we do it carefully, we will see the log z come. Okay, so where does that log z come? I'm writing something, I don't know. But if you follow first principles, it will come. Okay, it's not there in U, right? So it should be there in S. It should be there in, because F is U minus TS. Okay, so this is for me these are the interesting ones. What is happening? Okay, so and what happens at 1 for G 5 by 2 of 1? Is it finite or infinite? It's finite. Okay, Gn of Z is finite for n greater than 1. That's easy to see because so Gn of Z, if you remember the sum formula, it goes like this, right? Z power L, L power N. Okay, so now if you remember your if you put it equal to 1, it is just 1 by L power N. So just the standard absolute convergence will tell you that N should be greater than 1. That's all. Okay, so 5 by 2 is also convergent. Okay. So I'll pause here again for questions.
There is a number density in the ground state is fixed. So does it depend on temperature?
It does. It does. Yeah, that is this picture, right? So I drew one picture here. So so the thing is that the way I wrote the formula, there's a lambda cube there, and the temperature is buried in that thing. There's also a temperature in Z, but okay. So now you can see as you reduce temperature, lambda is changing. So then, so coming back to this equation, which we were solving, yeah, this equation. So as what is happening is that this V naught is changing with temperature. So whatever doesn't fit into this has to go here, because this is not changing. Left hand side is not changing. So as you lower temperature, you should see until Tc it is 0, and after Tc increases, it's going to be dictated by how much of this is. So this is giving you some finite number for fixed T. So as you keep reducing Tc, we know that this will more and more will start going. So this is just a schematic diagram, but it captures what. Okay. Hopefully my the curvature is correct. That I don't know. Okay, I haven't proved that it is. So that's what this is saying.
So below TC, do we have to wait for some time to see the condensation, or it happens immediately?
Oh, here we are doing equilibrium thing. We are not talking about the time scale, etc. But like most experiments, I think you got to be patient. So I think the last step in the condensation for condensation to happen is to do laser cooling, bring the temperature down to some number, and then switch off the laser cooling. Okay, and then and let so at the end of the day, what is temperature? If you're it's just the it is the average kinetic energy. So now what is happening is that you kind of lose particles which are very fast, and you let the other things thermalize. So you have to wait till they thermalize. Thermalization time, I don't know how long it is. Okay, but I don't think it will be very like this thing. But you have to wait, and then all of a sudden you see this remarkable phenomenon, and of course through some other. I mean, it's not like you see. So there will be some other effect, which maybe some laser shining or something, which will make it show some effect, which you can probably even it's visual. Okay, and so that's what happens. So I don't know the time scale of all these things. So this is where the Nobel lectures and the math thing. Go to nobelprize.org and please read up the experimental setup.